Okay, so the title of my talk is, as you see, it's going to be Virginia Nuclear Energy Frontier Research Center. I think this title goes along nicely with the current situation back home. I'm actually wearing 3 hats for this presentation. Number 1 is Virginia Nuclear Energy Consortium Authority, which was established by the Act of Virginia Legislature at the beginning of this year. So I have been appointed for a 4-year term by Virginia Governor. So I'm using as my first hat. And then I have actually an international symposium on hydrogen in matter, which is a nonprofit organization. Well, hydrogen is everywhere, as you understand, and it affects everything, including us. And of course, my hat, Jefferson Lab, is my employer, where I get my money for paying the bills. So this is the outline of my talk. I'll give you a brief introduction about the authority and what it is meant for and what it will be doing. And then talk a little bit about the Nuclear Energy Frontier Research Center. This is a kind of a dream at this stage, and we will see how it comes to reality. And one of the applications of this technology that you are trying to utilize for the ADS, that is the superconducting radiofrequency technology, can also be used for producing nuclear medical isotopes, some of them very efficiently compared to cyclotrons or proton machines. And then I end up with a small summary. As I mentioned, the Virginia Nuclear Energy Consortium Authority is established by the Virginia General Assembly recently, and it is effective since July 2013. And this authority is expected to create a nonprofit Virginia Nuclear Energy Consortium, which will be established by January 2014. And the VNEC Consortium will foster strategic partnerships to expand the nuclear energy business sector in Virginia. This is the main purpose of this, as well as training future generation of engineers and scientists in these new technologies. As you know, probably Virginia is one of the only 2 or 3 states which has a large number of and broad variety of businesses and institutions that are involved in nuclear energy. The stakeholders of Virginia Nuclear Energy Consortium Authority are shown here. And this has a no pointer. Is there a pointer to this? No. Oh, I see. Oh, okay, sorry. Not working? All right. It's not working, I guess. Okay. The stuff that was in blue are the nuclear energy industry, Areva, Babcock, Wilcox, Vestal, Luminia, Virginia Power, which generates 60% of Virginia's power from the 4 nuclear reactors at 2 sites, and they're also planning to build another new reactor. Huntington Ingalls is a Newport News shipbuilding very close to our lab, and that builds the only company that builds the nuclear-powered submarines as well as the ships that are floating aircraft carriers. So you can see how much we have around. The American, of course, the affiliate. And there are 2 universities in Virginia that have started nuclear engineering programs in the last couple of years. One is Virginia Commonwealth University, and the second one is Virginia Tech. Virginia Commonwealth University is located in Richmond, the state capital. So these are the broad goals of the Virginia NEC, which is going to be established in January of next year. It will try to bring all the nuclear industry players as well as the educational institutions together to expand the nuclear industry in Virginia across the country and hopefully around globe. And also to maximize the return on Virginia's investment in nuclear energy, higher education, and research initiatives by facilitating partnerships and collaborative programs between and among Virginia higher education and the private sector of nuclear energy-related research. This is a tall goal for this nonprofit organization. And also, it is expected to assist and support successful application for federal grants for the nonprofit as well as the university system. And Virginia Nuclear Energy Authority has 17 board members, and out of which 7 are the public universities and other establishments. These are the permanent members. And it has 10 other board members that will be appointed for terms by the Virginia governor. So what is the vision for the Virginia Nuclear Energy Consortium? We hope to create a science and technology center for the application of high-power accelerators for the advancement of innovative multidisciplinary science. And we hope that this will lead to establishing a Virginia Nuclear Energy Frontier Research Center. This is one of our dreams, and we are working towards to accomplishing that center within the next 2 to 3 years. This center would foster integration of education and training in all aspects relevant to the application of high-power accelerators for the advancement of innovative multidisciplinary science, and also to educate a new generation of highly qualified professionals in the area of science and technology covered by this center. And also, we would like to explore and leading the forefront research to explore materials and cavity designs to push current linear accelerator limits in order to achieve the technical and cost requirements. Basically, you need to cut down the cost of these ADS systems, and we will be able to do that very effectively, and I will show you some of the results that are already coming out. We also will be integrating the target analysis to speed up the development of targets for specific medical isotopes, waste processing, and power generation applications. And the center also would evaluate the chemical processing infrastructure required to take advantage of the output of ADS systems for new medical isotopes and other applications. So, who are the expected members of this center? These are there are several corporations involved here, as well as national labs and the universities. And they're also from outside Virginia, as you can see. So we have certain long-term goals, which I explained. And what is our immediate focus? Our immediate focus is something that we can help the society in developing nuclear medical isotopes that are something different from what you have right now. I will try to explain that as we go along. And this technology could be the entry vehicle so that we can show early success with the accelerator systems for practical applications. So this gives you an idea of how one could produce nuclear medical isotopes using CW electron linacs. You have a target in the center there, which will produce not only neutrons, but also gamma radiation. And that gamma will hit the target, and that will produce, as a result of photonuclear reactions, the required medical isotopes. And though there are a lot of room temperature electron linacs that are pulsed available, and that technology was unable to deliver certain nuclear isotopes which are really needed by the community. For example, copper-67, which was approved by the Federal Drug Administration about 25 years ago, could not be produced in the purity and the quantities required for human trials, and we believe this technology could change that. And so to get these continuous electrons, you need the technology known as superconducting radiofrequency technology. And the basic structure of accelerator structure is shown here, a multicell cavity which is made out of niobium. And these are the steps. You basically take a sheet of niobium and form into half cells, and they are electron beam welted into multicell cavities. And this is the example of the spallation neutron system in Oak Ridge National Laboratory. We have built those things at JLab. And these are the process steps. If you use the current technology, which is the high purity fine grain niobium, you have about 15 steps in getting this material. And during any of these steps, one has an opportunity to include impurities. As a result, you have to go through QA steps, so the material cost is very high. On the other hand, if you take the ingot niobium that comes from the source, in this case, the CBMM mine in Brazil, you get from the ore to the final metal at the same source, same company, and you can use these slices from these ingots. If you do that, you can cut down all these process steps, so the material cost will be pretty low in this way. Maybe it could be 1/3. I give you an example of the current status of this technology. This is the performance characteristics of the accelerating structures made out of niobium. The bottommost curve is the technology developed during the last 10 years by International Linear Collider Community. This, I think people have spent several tens of millions of dollars to improve the technology to whatever we got. That is shown here, which is a function of gradient, the quality factor. Quality factor basically determines how much heat loss in the cavity walls that needs to be removed by the helium refrigeration system. As you understand, these accelerator structures are operating at 2K. So the Q is very important. And of course, if you are using a pulsed Linux, you would like to get the highest gradient so that the construction cost will be lower. But the systems that we need for ADS applications will be CW systems. That means you want the highest Q possible you can get. So the accelerator gradient is not important in this case, because in a continuous wave mode, you cannot use more than 20 megavolt per meter, which is determined by the helium refrigeration system and the flow rates, etc. So if you understand that, of course, there are two technologies that we are showing here. The bottommost curve is the fine grain technology, which is current, and the squares, blue squares, is the technology based on the ingot niobium of the same purity. With the same processing conditions, you can see already there is an improvement, 60% improvement in the quality factor of these cavities. So that is very important. But if you go and use ingot niobium or low purity niobium, you see the curve in the middle stars that is using a low purity niobium made out of ingots. With a very simplified processes, you get a quality factor of something like 2.5 10 to the power of 10 at 1500 megahertz cavities for these cavities. So if you want to understand the difference between 1300 to 1500, you need to, the quality factor actually will be less compared to 1300. So already gaining something if you directly compare the curves that you are seeing there. Then the topmost curve is the new processes we developed with ingot niobium, where you get a quality factor improvement of 4 to 5 times. So this is Q improvement, and also the material cost of this material that I'm talking about, that is ingot niobium of low purity, will be at least 1/3 that of the current practice. So overall, if you use this technology for CW applications, you may gain an advantage of about a factor of 10, either both. That's what I think important about these new developments in this technology. So our goal for ILC is basically to improve that accelerating gradient. We have some kind of a collaboration that we are planning to develop with KEK in Japan, which is hoping to build the International Linear Collider over the next 10 years. So what is the future outlook with respect to the superconducting technology? The ingot niobium technology, that is using low RRR and high tantalum content. If you do this, the cost will be reduced by a factor of 3, has proven to be ideal for CWSRF applications. We expect this technology will be the preferred choice for future superconducting CW Linux worldwide. That means the ADS systems you are talking about here. And several labs from the 3 continents are discussing joint program to optimize ingot niobium multi-cell cavity processes for improving the efficiency even better than what we have right now for CW applications. So I mentioned about creating or generating or developing nuclear medical isotopes. This is a schematic of a system that will be able to produce nuclear medical isotopes using a 100 MeV electron linac. And in principle, you can get a power with such a system up to 1 to 2 megawatts. What you have here is a electron gun, which is a thermionic electron gun, about 200 keV at 1 or 2 milliamps, and a buncher, and a SRF cryo module, which we have produced several of those for our upgrade program at JLab. Thereabout each can give you energy gain of 100 MeV, and of course target on the dump. So this is an example of the thermionic gun we used to use at the beginning of our operations. And this is a 100 MeV electron linac that we have at least 12 of those in the lab, recently built. And we are hoping to develop this Virginia Nuclear Energy Frontier Research Center at a location next to Jefferson Lab, where a private industry is hoping to build the infrastructure, and they will lease the structure to anyone to set up this kind of facilities for R&D. And Newport News has approved this program, and the construction of the earlier part of the business is going to be probably started at the beginning of this month. And I already mentioned copper-67 was approved by the Federal Drug Administration for human trials about 25 years ago. The reasons being its half-life is about 2.58 days, and it's a beta decay mode. And basically, the maximum beta range in air is 200 centimeters, and in water is that. And you can see the parameters of these isotopes, the gamma emitting energies and all that there. As we understand, copper-67 is one of the best suited isotopes for radioimmunotherapy. And we have a group in Virginia Commonwealth University in Richmond, which are developing the antibodies. And they believe the dynamic growth of radioimmunotherapy applications can increase demand for this isotope. I have done some preliminary market analysis. From my personal investigations, I believe if you can produce this within 5 years, the demand, the market potential is about $1 billion per year in the United States alone. And here, the VCU Medical Imaging Group have come up some neat way of incorporating this kind of radioactive material, either in the core or outside, as you can see in B and C, and whereas the conventional stuff is shown in A. And they have a patent on this technology, and we are hoping to develop these systems in the next 5 years, hopefully. And the reason I'm here and the reason why I became part of this Thorium group is I met Dr. Banerjee, who used to be director of Bob Atomic Research Center in 2006. During the conversations, it became apparent that we have a technology that can benefit the thorium energy. And during one of his visits to University of Virginia in 2010, he presented this, which you have seen in different forms anyway. And you already know about these things. So this probably is important if you want to really develop this technology. the SRF technology, what we have with an improved quality factors, I believe you can get the neutron cost per gram if you use this new technology I just discussed, could be something like 110 to the power of 5 per gram. So as you know, 1996 there was a review of this technology for ADS applications, and at that time the committee felt this technology was not ready. And now if you go back and re-review, I'm sure that it is clear that this technology is more than ready for this application. And Hamid already explained his project, and we are hoping that he'll be able to use this new technology we have for this application. And these are the long-term goals of our research center I talked about. And I have given a priority of things from the top to the bottom. Isotope production, I think this could be implemented in the next 2 to 3 years if we have money. And that will help, one way of helping the community and give some payback for the tax dollars if we can do it quickly. And the 2, 3, 4, 5, 6, I think will be useful for this community as an R&D activities. Actually, we started ADS and thorium utilization international workshops in 2010, and the first one was organized by Virginia Tech, and the second one was hosted by BARC in 2011, and we are planning to host the third international ADS and thorium utilization October 14th, 17th of 2014, and the host will be the University in Richmond, VCU, and we are hoping that Virginia State will support this activity to the fullest extent possible. In summary, Virginia General Assembly, I think, establishes the Virginia Nuclear Energy Consortium Authority. I think this is a very futuristic initiative for this 21st century. And I hope that other institutions will follow to help this organization to create this future that we are all talking about in the nuclear energy area for R&D, as well as in educating future generation of scientists and engineers. And the ThEC Frontier Research Center is being planned to initially develop nuclear medical isotopes for imaging and therapeutic applications based on a 100 MeV CW SRF electron technology under the ThEC umbrella. So these are all some of our dreams, and hope there is some support to make this come true. Thank you very much for your attention.